Good evening, guys. Welcome to our project, Enhancing Image Understanding with Transformer-Based Image Captioning. We are Group 146. You may ask why image captioning. Image captioning is essential to understand and describe images accurately. Nearly 43 million people are visually impaired around the world. Image captioning is needed in assisting visually impaired people for better perceiving their surroundings. The current applications of image captioning include autonomous vehicles in navigation and e-commerce and retail. In autonomous vehicles, self-driving cars uses image captioning to understand the scene better and identify objects, pedestrians, and road conditions. It also helps in navigation aids to help visually impaired users navigate around spaces by describing the obstacles around them. E-commerce and retail. Apps like Google Lens and Amazon Visual Search allows users to take picture and receive a detailed description of the product. AI generated captions help influencers and business create better content. Our objective of the project, the traditional CNN and LSTM approaches struggle with long-range dependencies, while the transformers excel due to their self-attention mechanisms. Our approach is to develop a transformer-based image captioning model using a vision transformer to extract features from the image and a transformer decoder to generate caption. The dataset we'll be using is a Microsoft Common Object in Context dataset, which contains of 330,000 images, with each image having 5 human annotated caption. Understanding the inputs and outputs. The input will be giving are the RGB images from the MS Coco dataset and the text captions that are the 5 human annotated captions per image. The output would be caption generated of the like the description of the images generated by our transformer based model. And the evaluation scores we'll be using are Blue and Rogue to assess the caption quality. So these are the few visual sample images and caption. For example, you could see the image and the caption. Human annotated caption include a child holding a flowered umbrella, a young man holding an umbrella next to a herd of cattle, and so on. So during our EDA, we did a word frequency and using a word cloud, and words such as the friend, the table, group, top, man, water, etc. are the most commonly used words. Also,
So our baseline model is using CNN and LSTM. So CNNs are basically used for deep learning models for image processing. CNN extracts the visual images like colors, shapes, textures, objects, and etc. So we use a pre-trained model using an ImageNet dataset to generate features for each image. This CNN model basically acts as an encoder. So we combine this with LSTM, long short-term memory, which is a type of RNN that is designed to handle sequences. So LSTM acts like a decoder here. It receives the CNN's input as an image and then generates a sequence of words one by one and then forms and captions. So this is the performance of our baseline model. So you can see that the blue score is like 0.45 and the ROG is around 0.37. So this model has limitation. It often misses the context and struggles with complex scenes. So our baseline model generates the generic captions with limited variability, and the blue score is also low, which indicates a poor overlap between the ground truth captions. This also shows that the sentence often lacks frequency and relevance, and we have not used any attention mechanism, which limits the context awareness. So to improve on this, we used transformers. So transformers are a type of a deep learning architecture that is designed to handle sequence data. So there are three components, which is a self-attention mechanism, which allows the model to focus on the relevant features, the image or a text. And then positional encoding, since there is no recurrence or convolution, position encoding tells us the model order of the input. And the multi-head attention, this allows the model to learn different aspects of the input. So transformers are what make models like Vision Transformer GPT possible. So combining both is a foundation of our proposed image captioning model. So our approach uses two-part transformer-based architecture. First, we have the vision transformer for image encoding. It splits the image into patches and embeds them to tokens in a sentence. This allows us to treat image features similarly to how we process words in a sentence. Then we pass these features to the transformer decoder like GPT-2, which is trained to generate descriptive caption. The decoder learns how to associate visual patterns with natural language through training on image caption pairs. So this combination brings out the strength of both the vision and language transformer, which actually helps us to understand the fluent and the context-rich text generation. So this is the ground truth and prediction. So you can see the ground truth where the woman walking on a tennis court holding a racket matches a little bit with the predicted one, which is a woman holding a standing or holding a tennis racket. So the generated captions are often more fluent and context aware, than the baseline one, the baseline CNN plus LSTM approach. So our model captures the visual details better and construct more meaningful sentences. So the metrics here, we can see that the blue score is around 98%, which is a significant improvement. So this indicates our model is highly accurate in captioning the keywords and structure used by the humans. And ROG captures the longest common sequence, which is almost like around 40%. So which reflects the overall structure and the coherence of the sentences. So prior work, previously we have worked with neural networks, especially CNN and RNN. This hands-on experience gave us a strong foundation in the deep learning. So for this project, we are building on that by deep diving into transformer architectures. So these are the references that we have used along this project. So thank you.
Thank you.